Hey everyone. So there have been a lot of requests for this paper. So I'm solving May-June 2022 9702 variant 42 today. This is A-level physics, A2 physics. So I did paper 4.1 or 4.3, the previous video, and I plan to do chemistry after this, chemistry paper 4, alright? Followed by paper 5, sooner or later. So let's take a look at the threshold. What's it like? This is variant 42. I heard this was extremely difficult. So A was at 54, B was at 46, C was at 35, D was at 24, and E was at 13. Okay, let's begin. So A star, where would A star be at? It's probably around, 70-ish, around 70. Or even less, I'm not sure. So the syllabus did change starting from 2022. We no longer have band theory, magnetic resonance imaging, MRI. We don't have communications and operational amplifiers anymore, but instead astronomy was added, right? And discharging a capacitor was added. So let's begin. Define gravitational potential at a point. Okay, so this is a common definition that we get from time to time. So gravitational potential is defined as the work done per unit mass or you could write it together, work done to move unit mass, or this is how they word it. It's the work done in moving. Work done in moving unit mass from infinity to the point inside the field, okay? Starting from the equation of gravitational potential due to a point mass, show that the potential energy can be written like this. Okay, this is pretty uncommon. So guys, the formula for electric potential energy is del phi into m, okay? So we know that phi, gravitational potential, is minus gm by r, right? So this can be written as minus gm by r times m, which results in minus gmm by r. That's it. Okay. Figure 1.1 shows the path of a comet of mass 2.20 into 10 power 14 kg as it passes around a star of mass 1.99 into 10 power 30 kg. At point X, the comet is 8.44 into 10 power 11 meters from the center of the star and is moving at a speed of 34.1 kilometers per second. We're talking about this point. At point Y, the comet passes its point of closest approach to the star. At this point, the comet is a distance of 6.38 into 10 power 10 meters from the center of the star. Okay. Both the comet and star can be considered as point masses at their centers. Calculate the magnitude of the change in gravitational potential energy of the comet as it moves from position X to Y. So as it moves from position X to Y, since it's coming closer to the mass, it loses GP, right? So the change in gravitational potential energy is basically equal to del phi times m. Okay. So what's the final potential? the final distance is this. This is our final distance. So it's actually minus gm by 6.3 in 10 power 10 minus gm by 8.44 into 10 power 11. That was our initial distance, okay? And the whole thing should be multiplied by mass. Now, what we can do is we can actually take gmm common. So we end up with 6.67 into 10 power 11. That's the value of g. The value of capital M is 1.99 into 10 power 30, right? And the mass of the smaller, the comet, is 2.20 into 10 to the power 14. This multiplied by minus 1 divided by 6.38 into 10 power 10 plus 1 by 8.44 into 10 power 11. Okay, so let's do that. Oh, sorry, I made a mistake. It's 6.67 into 10 power minus 11, right? So this gives us an answer of minus 4.23 into 10 power 23. So they just want the magnitude though. It's 4.23 into 10 to the power 23. But what does the minus sign indicate? They only wanted the magnitude, right? But the minus sign indicates that has been a decrease in the potential energy. Okay, this is how you do it actually. So in the mark scheme, you might see that they've interchanged the positions. Basically, they might have added a plus sign with 1 by 6.38 and a minus sign with 1 by 8.44. But I did it in the original method. This is how we find out the change in gravitational potential energy with the sign. Okay. Why 3 significant figure answers? Because everything I used was to 3SF. State with the reason whether the change in gravitational potential energy is an increase or a decrease. Oh, here we go. So, it's a decrease. Why? Mainly because gravitational force is an attractive force. So if two masses come together, GP decreases. So gravitational force is attractive. So decrease. Or you could say that the gravitational force does work. Okay, so decrease. All right. Use the answer to determine the speed. Okay, so since GP decreased, kinetic energy increased, right? So we can say that the change in electric potential energy is equal to the change in kinetic energy, right? So we had our answers 4.23 into 10 to the power 23, right? That was actually converted to an increase in Ke. Our particle already had kinetic energy initially, right? 34.1 kilometers per second, which is 30. Okay, wait. So half m v square minus u square. So we want to find out the final speed. So 4.23 into 10 power 23 is equal to half times the mass of the comet, which is 2.20 into 10 power 14 times v square minus 34.1 kilometers per second, right? That is actually 34.1 into 1000 or into 10 to the power 3 whole square. Okay, so let's solve this. So 4.23 into 10 power 23 times 2 divided by 2.2 into 10 to the power 14. Okay, plus 34.1 into 10 to the power 3 whole square. Okay, Okay, wait a second. Okay. So I'm getting an answer of v square is equal to 5.01 into 10 to the power 1, 2, 3, 4, 5, 6, 7, 8, 9. But if you root over the answer, 2, 3 significant figures, we're getting an answer of 70800 kilometers per second. Okay. Oh, this is meters per second. So if you want to convert this to kilometers per second, you have to divide this by 1000, right? So we're getting an answer of 70.8. Okay, 70.8 is. Next, a second comet passes point X with the same speed as the comet in B and traveling in the same direction. The comet is gradually losing mass. The mass of this comet when it passes point X is the same as the mass of the comet in B. Such is the reason how the path of the second comet compares with the path shown in figure 1.1. So our comet is actually losing mass. Okay. This is the second comet. So here's the thing. This was actually a trick question. What will happen to the velocity? The mass remains unchanged. Do you know why? Because check this. We know that the gravitational potential energy is actually equal to the change in K. This is m del phi into m, which I wrote initially, and this is half mv square. So both of them actually include mass, right? So mass is actually cancelled out at the end. So it doesn't really matter. Even if mass changes, it will remain the same. So both potential energy and kinetic energy equations include m. So path is unchanged. There was a similar question in ON 2021 on centripetal force on mass, the effect of mass. Okay, so moving on to question number 2. State Coulomb's law. So Coulomb's law states that the electric force between 2-point charges is proportional to the product of the charges and the force is inversely proportional to the square of their separation. Positronium is a system in which an electron and a positron orbit with the same period around their common center of mass as shown. Okay, this is positronium. We have an electron and positron. They're antiparticles of each other. The radius r of the orbit is 1.59 into 10 power minus 10 meters. Explain how the electric force between the electron and the positron causes the path of the moving particles to be circular. So what are we seeing? Essentially, basically, this is a circular motion. So the force between the electron and the positron is attractive, right? The force is towards the center. Also, if you want to find out the direction of the velocity, do you guys know what it is? It's actually a tangent at a certain point. So this is the direction of the velocity and this is the direction of the force. Are in the perpendicular to each other. So whenever force is perpendicular to velocity, you will get a circle. Now, why is it a perfect circle and why isn't the radius decreasing? Because the magnitude of the force is constant. If the magnitude changes, it becomes a spiral. So we need to mention those things, okay? So we need to say that the electric force is perpendicular to the velocity of the particles. So the last mark was for like many things. You could say that the force causes centripetal acceleration. Or you could say that the force does not change the speed of the particles. Or you could say that the force has constant magnitude. Okay, that works. That's the requirement for the second mark. Show the magnitude of the electric force between the electron and positron is this. Okay, so we're going to use Coulomb's law. F is equal to 1 by 4 pi epsilon naught into q by r square. Here both q's are in fact e, the elementary charge, right? So it's actually e square by r square. So the r, we can't actually write r because r is the radius, right? And this r that I meant is the distance between them. So why don't we call it x, right? The distance between them, let that be x. So F is equal to, this is 8.99 into 10 power 9. So elementary charge is 1.60 into 10 power minus 19 whole square times the distance between them. So this is the radius of the orbit. So the distance between them should be double this value, right? 2 into 1.59. So that's divided by 2 into 1.59 into 10 power minus 10 whole square. Okay, let's go for this. So apparently the mark scheme, they didn't use 8.99 into 10 power 9. That's really weird though. Is that in the data sheet anymore? Yeah, it is. You can use it. It's fine. Okay. 8.99 into 10 power 9 into 1.6 into 10 power minus 19 whole square by 2 into 1.59 into 10 power minus 10 whole square. So it is in fact 2.28 into 10 power minus 9 shown. Alright, great. So for show questions, we need to carry this forward. Use the information in B2 to determine the period of the circular orbit. So we know that the electric force provides the centripetal force, right? So we know that the centripetal force is m v squared by r or m omega square r, right? So the force, basically the electric force provides the centripetal force. So 2.28 into 10 power minus 19, sorry 9 is equal to m omega square r. Now here r is the radius of the orbit and omega is equal to 2 pi by t. We know that, right? Omega equals to 2 pi by t. So 2.28 into 10 to the power minus 9 is equals to m times 2 pi by t whole square times r, or 2.28 into 10 power minus 9 is equal to 4 pi square mr divided by t. This is it. By t square, yeah. Now what? Following this, we need to make t the subject. So t square equals to 4 pi square. What's the mass of an electron or positron? It's 9.11 into 10 power minus 31. It's in the data sheet. The mass of an electron, I just have it memorized. The radius of the orbit was 1.59 into 10 power minus 10. Okay, divided by 2.28. Okay. So t square is 2.51 into 10 power minus 30. So if we root over that, I'm getting an answer of t is equal to 1.58 into 10 power minus 15. um, to 3SF because the data is in 3SF, right? Positronium is highly unstable, and after a very short period of time, it becomes gamma radiation. So this thing, when a positron and an electron comes together, or when a particle and its antiparticle interact, this interaction is called disintegration. We see this in PET scanning. Okay. So one medical application is in fact PET scanning. Interesting. And so describe how gamma radiation is formed. Let's see. Mass is basically converted to energy. Okay. Disintegration, or this is called annihilation. So the electron and positron interact, and the electron is the positron is the antiparticle of the electron. I told you this at the beginning. So this thing is called pair annihilation. So pair annihilation occurs. All right. So ultimately, you need to say that mass is converted to mass of whom exactly? Mass of the electron and positron. Mass of electron and positron is converted into photon energy. Understood? So this is 1 mark, and you get 2 marks for writing any two of these. So if you write the first three, you aren't getting full marks. Okay. So see if you understand. We had similar questions in the specimen paper in March of 2022. Okay, so you can check those out. All right. Okay. For 3, we have define specific latent heat of vaporization. So what is this? This is mainly the thermal energy required to change the state per unit mass, right? Or of 1 kg between liquid and gas. The thermal energy per unit mass, thermal energy required per unit mass, sorry, to change the state between, since it's vaporization, between liquid and gas. At constant temperature, right? There you go. So the specific latent heat of vaporization of water at 8 atmospheric pressure is 1 into 10 power 5 pascals. Of is this. The mass of 0.37 kg of liquid water at 100 degrees Celsius is provided with thermal energy needed to vaporize all the water. Calculate the thermal energy supplied. So we know that Q is equal to ml, right? So the value of m is 0.37 kg and the value of L is 2.3 into 10 power 6. So we end up with an answer of 8.5 into 10 power 5 joules to two significant figures at constant temperature, by the way. The mass of 1 mole of water is 18 grams. Assume that water vapor can be considered to behave as an ideal gas. Show that the volume of water vapor produced is this. Okay, so we're going to go for PV equals to nRT. So PV equals to nRT. The pressure is 1 into 10 power 5 pascals. This is the pressure, right? So what about the volume? The volume is, oh, we don't know the volume. What about the moles? Moles equals to mass by mR, right? So the mass is in kg. So always convert mass to kg except moles. You need to keep it in grams there. So 0.37 kg is basically 0.37 times 10 power 3, which is 370 grams, right? So 370 by the MR molar mass, which is 18, that's N. The value of R is 8.31 given in the datasheet, and the temperature is basically 100 degrees plus 273 Kelvin, which is 373 Kelvin. Yeah. So what's our answer? 8.31 times 373. 0.638, 0.637, which is 0.64 meter cube. So as usual, this is a show question, so we need to carry this forward, not the calculator answer. Assume that the initial volume of the liquid water is negligible compared with the volume of water vapor produced. Okay. Determine the magnitude of the work done by the water in expanding against the atmosphere where it vaporizes. Okay. So we know that the work done for a gas, we use the the formula work done equals to P del V, right? So the pressure is constant at 1.0 into 10 power 5. And what about the change in volume? So the initial volume, it was from liquid to gas, right? So they told us to consider the initial volume to be negligible, which is 0, and it became 0.64 meter cube, right? So it's basically final volume 0.64 minus 0, which is 1.0 into 10 power 5 times 0.64. How much do we get? 96,000 joules. Okay, next. Sorry, I made a mistake in the calculation. 64,000. Or 6.4 into 10 power 4, yeah? Next, use the answers in B1 and B3. Which ones? B1, the thermal energy supplied, and this. Okay, okay. So we're talking about internal energy. Let's talk about the first law of thermodynamics. What does the first law state? The change in internal energy is equal to the work done on the system and the thermal energy supplied to the system. So they want an explanation, right? So basically thermal energy was supplied to the system since it's boiling, right? So that's going to be positive. And what about W? Since it expanded against the atmosphere, we are working against the atmosphere, so work done is actually negative, right? So the reasoning is water does work against the atmosphere. Okay, so work done on water is in fact negative, right? And Q is positive because thermal energy is supplied to the system. So del U is equal to minus 64,000 minus 6.4 into 10 to the power 4 plus the thermal energy supplied, which was 8.5 into 10 power 5, yeah? I'm getting a value of 786,000, which is basically 7.9 into 10 power 5, yeah? 7.9 into 10 power 5, all good. Use the first law of thermodynamics to state with a reason how the specific latent heat of vaporization at a pressure greater than atmospheric pressure compares with its value at atmospheric pressure. Okay, so listen guys, we know that work done is P del V, right? So as you increase the pressure, the work done to vaporize will be more. So more work will be done by the gas, and as a result this value will become more negative. So as it becomes more negative, what's the problem? As it becomes more negative, the value of del U actually decreases. Okay, so as the value of pressure increases, the work done against the atmosphere will also increase. So what will happen to the value of the latent heat? Okay, let's try to understand. So the first law states that del U is equal to P del V, the work done by the gas, and plus ml. Okay, ml basically. So some things remain unchanged here. Okay, some things remain unchanged. What does specific latent heat state? It's the amount of thermal energy required per unit mass to change the state between liquid and gas. So at higher pressure, it actually becomes, more specific. More heat is required to change the state, or we can say that the specific latent heat is higher at higher temperature. Why is that? Because more pressure is exerted, so we need a higher boiling point. The boiling point increases basically. Why is that? Because the liquid actually boils when the vapor pressure exerted by the liquid is equal to the atmospheric pressure. Okay, so but using the first law of thermodynamics, we can actually state that since the value of pressure increases, this value as a whole, right, it becomes more negative. But we need this same increase in internal energy. We need this value to change the state. Do you guys understand? So how can we achieve that? How can we achieve that for the same mass of gas? So let's see the reasoning. So at a pressure greater than atmospheric pressure, work done by water is lower or more negative. Okay, so we get 1 mark for that. This is the first mark. Now, for the second point, they state that correct use of first law to draw a conclusion about effect on specific latent heat that is consistent with work done. So, since this is negative, just think about it. We know that del U is equal to P del V plus ml, right? So, since this becomes more negative, what's going to happen when you move it to that side? We can write that ml is equal to del U minus PV. So minus minus makes this value positive, right? So this value as a whole is going to become more positive, or this whole thing is going to become more positive. And for the same mass of gas, if you cross multiply, L is equal to del U minus PV, P del V divided by M. So the numerator is basically increasing. Okay, so we can say that the specific latent heat of vaporization is greater at higher pressure. Then you can just show this equation. You can show that L is equal to del U minus P del V divided by M, where del U minus P del V has a higher positive value. Okay, you can state that. Or you can just say that ML, ML has a higher value because we stated that the work done by water is more negative. So there is already a minus sign before P del V, so the value becomes more positive as a whole. So del U minus P del V is a higher positive value. Okay, so that's that. This was a bit tricky, right? So in fact, at higher pressure, a greater temperature or more work needs to be done to achieve the same increase in internal energy. Do you guys understand? That's the issue. Okay, that's all. Moving on to number 4. Okay, so what is meant by resonance? Basically, when the driver frequency is equal to the natural frequency of oscillation, there's increased amplitude of oscillation. That phenomenon is resonance. So we state like this: the oscillations of an object at maximum amplitude when the driving frequency or the drive frequency is equal to the natural frequency. Okay, that's all. Figure 4.1 shows a heavy pendulum and a light pendulum, both suspended from the same piece of string. The string is secured at end to fixed points. Both pendulums have the same natural frequency. The heavy pendulum is set oscillating perpendicularly to the plane of the diagram. Okay, so it's set to oscillate so that it, uh, you know, oscillates perpendicular to the plane of the diagram. So in and out of the page, basically. This is the plane of the diagram. So it's going in and out of the page. And since it's so heavy, it's also causing, you know, oh, this is so interesting. The heavy pendulum is basically applying a driving frequency on this string, which is causing the light pendulum to oscillate as well. Okay. So as you can see, it's like this. The variation with t of the displacement x of the light pendulum is given by this equation. Calculate the time period of oscillation. Okay. So x is equal to 0.25 sine omega t. This is another way of saying this, right? So what is this omega equal to? 5 pi is actually equal to omega. Does that make sense? Right. So can't we say that omega equals to 2 pi by t, or t is equal to 2 pi by omega, right? And we also know that omega is equal to 5 pi. So we can write that t is equal to 2 pi divided by 5.0 pi, and we end up with 0.40 seconds. No 1SF answers, only 2SL, okay? Now on figure 4.2, label both the axes with the correct scales. Use the space below for any additional working that you need. Okay, so wait, what? With the correct scales. Oh, okay, they mean the numbers, right? So basically, this is the variation of the light pendulum. The value in front, this is the amplitude of oscillation. Do you guys understand? And this t over here, this is the time period. This is the time period for one complete oscillation. Could I clarify? So for one complete oscillation, we need 0.4 seconds. So this is 0.40, then this is 0.8, and this is ultimately 1.2. Similarly, this is 0.2, this is 0.6, and this is 1.0, right? Next. What about the scales? So this maximum amplitude, this is 0.25, right? As you can see from the info, 0.25 centimeter. So this must be 0.50 centimeter, right? Then this is 0.75 cm, and this is 1.0 cm. Similarly, this is minus 0.25, minus 0.50, minus 0.75, and minus 1.0. Get it? Here you go. Great. So by the way, 0.25 and 0.5 were optional. Even if you don't do them, that's fine. Okay, but I'm gonna opt for that. Next. Why do we even need this space? Determine the magnitude of the phase difference phi between the oscillations of the light and heavy pendulums. Give a unit with your answer. Interesting. Interesting. So I was going to talk about this, in fact, before we started the sum. So how are we going to find this out, really? It's a bit tricky, but we can do it. So both of them have a time period of 0.4 seconds, right? We need to compare common points. We need to compare common points. They are clearly not in phase, they are anti-phase. So you could do the sum in two ways. So we've done this in AS waves, okay? So for example, if I consider the starting of the lighter pendulum here and the starting of the heavier pendulum here, how much is the phase difference really, guys? One small box, two small boxes, three small boxes, right? Wait. So basically it's this distance over here, this one. So that's one, two, three small boxes, 0.3. So that's 0.3 because both of them are starting their wave just from here, right? So it's 0.3 boxes. So they wrote the formula like this. It's 2 pi del t by t. What does this mean? Basically, I told you the phase difference is 0.30 seconds, right? Three boxes. Divide by the total time period, which is 0.40 seconds. And if you multiply it with 2 pi, you're going to get the answer. So that gives us an answer of 3 by 4 into 2 pi, which is to 2SF 4.7. 4.7 rad. Okay? So 4.7 rad. Or guys, what's another way of thinking of it? They actually allowed both. What if you want to think of it this way, you know? What if you want to think of it this way? For example, you're thinking that, okay, the waves are starting here. This wave is also starting, this wave is also starting. What's the phase difference? It's just a single box, right? Just a single box that is 0.1 seconds out of phase, 1/4 basically, right? So 2 pi times this, 2 pi into 1 by 4 is basically 1.6 rad. 1/4 basically it's essentially you know 2 pi by 4, which is 90 degrees out of phase. Okay, 1.6 rad. For some reason they didn't take 90 degree. Like that's what I wanted to tell you guys before starting the experiment. It clearly looks like it's one it's one box out of phase if you think of it here. So that's pi by 2 radians, 90 degrees basically, but they wanted it to be done this way using math. Okay, so you don't find this quite often. This is new. All right, moving on to number 5. Define capacitance. Capacitance is defined as the charge on one plate divided by the potential difference across the plates. All right. Alright, so for part B, we have two capacitors of capacitances C1 and C2. They are connected in parallel to a power supply of EMF E as shown in figure 5.1. Alright, so we know that in a parallel circuit, the voltage will be the same for C1 and C2, but current will actually split into two parts. So the sum of current entering a junction is equal to the sum of current leaving the same junction. So basically I is equal to I1 plus I2, as you can see in my diagram. So we know that for parallel capacitors, the total capacitance is actually the sum, right? It's the sum of the capacitance. So to show that, we need to use Kirchhoff's first law, right? So we know that according to Kirchhoff's first law, the total current is equal to the sum of I1 plus I2. Now we know that the first law, for Kirchhoff's first law, follows the law of conservation of charge, and you guys need to remember that um, charge bears a it has a connection with current basically, because we know that Q is equal to IT, or I is equal to the rate of flow of charge, right? So we can substitute Q here instead of I. So we end up with the total charge into interjunction is equal to Q1 plus Q2. Now we also know that C is equal to Q by V, or Q is equal to CV. This is our relation. So we know that for all of them, the voltage is the same, or we should say the EMF, E. Here both C1 and C2, they are getting E. As a result, we can write the total capacitance into EMF is equal to C1 into E plus C2 into E. So we can get rid of E, and we ultimately end up with CT is equal to C1 plus C2. So you need to learn this, as well as the total capacitance in a series circuit. You also need to learn that, alright? Moving on to question number C over here. This is an important one. I actually had this question done beforehand. It's fine though. So let's begin. Two capacitors of capacitance is 22 microfarad and 47 microfarad, and a resistor of resistance 2.7 mega ohms are connected to the circuit of figure 5.2. Alright, so the battery has an EMF of 12. Show that the combined capacitance of the two capacitors is 15 microfarad. So since they're in series, we need to add the reciprocals. We need to add the fractions and then reciprocal. So it's basically 1 by 22 plus 1 by 47 to the power minus 1. You get an answer of 14.98, which is approximately equal to 15. So that's the first part, right? So we have a two-way switch S, which is initially at position X, so that the capacitors are fully charged. Okay, so initially the switch is over here. So it's kept in such a way so that current is flowing like this, and the capacitors are fully charged up. So since it's a series circuit, the current will be the same, however the voltage will differ. Use information in C1 to calculate the total energy stored in the two capacitors. So we know that the energy stored is half CV square, or half QV. We typically do not use half QV, we opt for half CV square. Okay, so the total capacitance is half CV square. So sorry, the total energy is half CV square, while the total capacitance is 15 microfarad. So we're going to write down the formula as half CV square. So we're going to end up with half into 15 into 10 power minus 6. I converted the 15 microfarads to farads, and the voltage, like, we can consider the circuit, even though there are two capacitors. Let me draw a diagram. We can actually consider this scenario, like this battery. It's actually connected with one capacitor, which has a total capacitance of 15 microfarad. This is basically it. This is what I'm considering. So the energy is half CV square, essentially half into 15 to 10 power minus 6 into 12 square. Could I clarify? Which gives us an answer of 1.1 into 10 to the power minus 3 joules. All right, that's part 2. Sorry for my long hiatus, by the way. I've been extremely busy. I didn't get the time to record any videos. A part of it was already recorded beforehand, by the way. I'm recording this on a later date. Um, I'll try to do as many videos as possible. I know you have your October-November exams coming up, but I mainly focus on the May June series. But I'll try my best to complete the other papers as well. Right. Number 3, the two-way switch is now moved to position Y. Interesting. So my students, the ones who gave the exam this May June, they were actually confused about this part 3. So it's rather complicated. So initially the capacitors were charged up. Now what happened? We actually moved this switch from position X to position Y. Now what? Basically current can no longer flow through this. Now current actually flows in this direction. So basically the capacitors will discharge, and because they're connected across this resistor in series. So we know that we have to use the formula V is equal to V naught e to the power minus t by RC. This is the formula for discharging a capacitor. Alright, so we first need to know the notation. What does each thing mean? V naught is the initial voltage of one component, or like the capacitor, the whole capacitor. Like you can think of it this way: the 15 microfarad capacitor. V is the final voltage of that component. E is exponential. T is the time taken. R is the total resistance of the circuit. Okay, and C is the total capacitance of the circuit. It's the total capacitance and total resistance. A lot of students did not know that, which is why they made a mistake. So let's begin. Determine the time taken for the potential difference across the 22 microfarad capacitor. They are specifically talking about this one, to decrease to 6 volts. Okay, so it became 6 volts, but from what exactly? We need to find out the initial value, right? We don't know the initial value. Let's try to figure that out. So let's see. So in the mark scheme, they opted for a very quick method, which is this. The initial voltage across the 20 microfarad capacitor is 12 into 15 by 22. You can do this if you guys want. You can do this if you guys want. Which gives us an answer of 8.2 volts or 90 by 11. So how did they come up with this exactly? What's the logic behind this? So this is basically V1 C1 is equal to V2 C2. They applied this method. V1 C1 equals to V2 C2. So initially, if you think about it, when we considered them to be one whole capacitor, the capacitance was 15 microfarad and it was getting 12 volts, right? So that's your V1 and C1, 12 times 15, right? And that's V1 C1. What about V2 C2? We don't know the initial value of voltage of the 20 microfarad capacitor, but we do know its capacitance. It's actually 22. So V2 is basically 12 into 15 by 22, right? 12 into 15 by 22, which gives us an answer of 8.2. So that's what they did in the mark scheme. I can show you a more detailed method though. Let's see how it came to be, right? So this is the circuit. This is the initial circuit. So we know that in a series circuit, the current is constant, but we don't typically use current in capacitors. We use charge. We know that Q is constant. So we can find out the total charge stored on each plate using Q is equal to CV. So I use the total capacitance. So the total charge is actually um, QT is equal to 15. Total charge equals to 15 times 12, which is 180 microcoulomb. So that's the basis of C1 V1 equals to C2 V2. Because since this is a series circuit, the charge stored on each plate of all the capacitors will be the same if you consider them individually or if you consider them as one capacitor. Do you guys understand? So we end up with 180 microfarad. So this 180 microfarad is actually stored on the plate of 20 microfarad capacitor, 47 microfarad capacitor, as well as this capacitor over here, right? Now we can apply Q is equal to CV again. So I did that over here. So we end up with 180 Q is equal to CV. 180 microfarad is equal to, sorry, microcoulombs. 180 microcoulombs I meant. 180 microcoulombs equals to 20 microfarad into volts. So 180 divided by 22 is in fact 8.2 volts. So that's the logic behind this, alright? So that's our initial voltage. It was 8.2 volts. Now it became 6. Now we can finally input this in the formula. V is equal to V naught e to the power minus t by RC. So the initial voltage is 8.2 or 90 by 11. The final voltage is 6 into e to the power minus t by RC, where the resistance in the circuit is 2.7 into 10 power 6 ohms, mega ohms. And the total capacitance, this is where the students messed up. You need to apply the total capacitance. Even though we're dealing with the 22 microfarad capacitor, you need to use the total capacitance because both the capacitors are involved in discharging, alright? So we have to use 15 into 10 to the power minus 6, the value we found out in part 1, alright? So if you do solve this equation, after cross multiplication, we end up with 66 is equal to 90 into e to the power minus t by 40.5 after you multiply 2.7 into 10 power minus 6 into 15 into 10 power minus 6. Basically, the 10 power 6, we can get rid of those two. We can get rid of this one as well as this one. So it's 40.5. Now you introduce or you bring 90 to the left side and you introduce ln. So you end up with ln 66 by 90 is equal to minus t divided by 40.5. Ln e gets removed and the power comes down, right? So after you solve this, you get an answer of 12.56 seconds, or it's 13 seconds, yeah, to two significant figures because the data is in 2SF. There was an alternate way in the mark scheme. Let me teach you that as well. It's a more complicated process where rather than considering the voltage of one component, we actually consider the voltage of both the components combined. For example, we know that initially, like if we consider both capacitors to be one capacitor, we know that the total voltage will be 12. It's taking up all of it. But what happens after a certain time? Like we know that the 22 microfarad capacitor has a voltage of 6, but what about the 47 microfarad capacitor? Can we find that out? Of course we can. Check this. This is method number 2. You can also use this if you want. The final voltage of the 47 microfarad capacitor, I applied the same thing. C1 V1 equals to C2 V2 because it's a series circuit. 22 times 6. Like, why can I do this, by the way? Because I am considering the time where the 27 microfarad capacitor has 6 volts. So it has a capacitance of 22. So if it has, it's a series circuit, right? So the charge here will be the same as charge here. We know that Q is equal to CV. So we can say that 22 times 6 is equal to 47 times um, a certain voltage because it's a series circuit and charge be conserved, right? So I did that. 22 times 6 equals to 47 times V. We end up with a voltage of 2.8. So what's the final voltage at that time if we add them up, since it's a series circuit, Kirchhoff's second law? It's actually 2.8 plus 6. 6 from this, the part given in the question, and 2.8, the one we found out. So 8.8. So initially the circuit had 12 volts in total. The capacitors had 12 volts in total. But now it's 8.8 combined. Now we can apply the formula again. V is equal to V naught e to the power minus t by RC. 8.8 equals to 12 e to the power minus t by same resistance and capacitance. You're gonna get the same answer. Personally, I prefer the one on the left hand side. Okay, this also works. There's another route you could take. You could only consider the 47 microfarad capacitor. Okay, like you can find out its initial voltage. Since this took up 8.2 initially, this one would obviously take up 12 minus 8.2, which is 3.8 volts, right? Obviously. And yeah, from 3.8 volts, it became 2.8. You could use that as well. You'd get the same answer, right? So moving on to question number 6. How many do we have left? 2, 6, 7, 8, 9, 10. Okay. So we're done with half the paper, I'm assuming. Number 6. State the conditions that must be satisfied for a copper wire placed in a magnetic field to experience a force. We know that F is equal to BIL sin theta, right? So to experience a force, it must have current flowing through it, okay? So there must be a current in the wire, right? Also, um, it must not be parallel to the field lines. It must have an angle with the field line, because we know that it's BIL sine theta. So we actually take the perpendicular component, yeah? So the wire must be at a non-zero angle. Basically, it can't be parallel to the magnetic field. All right, those are the conditions. Also, guys, there was a question of magnetic field in variant 4.1, which I wasn't sure of. Okay, I'm gonna provide an explanation for that at the end of this video. Right, I'm gonna give the timestamp down below. Okay, so a long air core solenoid, so it's hollow, is connected to a power supply. So the solenoid creates a magnetic field. So figure 6.1 shows a cross section through the middle of the solenoid. All right. So for example, if this is your solenoid, and suppose the wires are like this. So we have cut it in this section. We've cut it in this section. So we've taken that part away. So we are viewing the cross section basically, right? Because it was cut through the middle essentially. Okay, if you view the cylinder from the top, it was cut like this. As a result, we are seeing the cross section right now. Okay, so we're gonna see through the wires essentially. The direction of the magnetic field at point W is indicated by the arrow. 3 other points are labeled X, Y, and Z. So the magnetic field is in this direction. So basically, you guys need to know that the field comes out from the north side. So this is the north side and this is the south end, because the field line, since it's pointed in this direction, it's going to come out from here. Okay, and it's going to enter this point. So it's like this basically. So the field lines are like this. My bad. Here you go. This is what it looks like. Okay, so we know the north and the south pole now. On figure 6.1, draw arrows to indicate the direction of the magnetic field at each of the points X, Y, and Z. Interesting. So I'm going to show you the actual drawing. This is what it looks like. Okay, so inside the solenoid, there's actually a uniform field. Okay, it actually looks like this over here, and basically it's gonna be like this as you head out. Wait up here, like this. Okay, similarly it's gonna be like this over here. It's gonna enter into south. What about at Z though? Basically what happens at Z is basically if I draw the field like this, another line, suppose if there's a field line over here, it's basically gonna curl around over here. It's gonna curl around over here and enter this side like this. It forms a field like this. Okay, so this is the field line. It's gonna come out from here, curl around, and come back in. So if you match my drawing with what they want, we get the answer. So I'm gonna do point X first. So for point X, it should be a horizontal line to the left according to my drawing. Okay, so the one at Y, this looks good. My drawing here looks good for Y. It looks fine. It's gonna be like this. In the mark scheme, they mentioned a line pointing, 45 degrees um, upwards and to the left. It matched with my drawing. And the one at Z, the arrow should be pointing to the right, and that matches with the mark scheme. Okay, so this is basically it. Okay, this is your answer. So tell me if you do have any queries still. So the one at X points to the left, the one at Z points to the right horizontally, and the one at Y is diagonal. All right, is that fine? Next, compare the magnitude of the flux density. Interesting. So basically, I told you something, that inside the solenoid the field strength is uniform. How do you guys know that? Basically, the field lines that I draw, they are in fact equidistant. Equidistant field lines in fact refer to equal field strength, so they are approximately equal. Clear? They are approximately equal. So at x and w, I mean, so they are approximately equal. Flux densities are approximately equal. Okay, but what about y and z? Clearly, guys, check this. Um, Here, once you come out, it's gonna be like this, right? So as you come out from the solenoid, field strength decreases gradually. Okay, so if you compare this position and this one, the strength is actually determined by the difference in field lines. So here what happens when this crosses over here, when it curls around, check out the difference between the field lines over here and here. Here it's not that far away from this field line, right? But here the distance is quite, it's quite big. And in fact, the strength is minimal over there. It's very less comparatively, right? So it's actually very low over there because it's in between the north and south pole, so the strength would be low there. Okay, so it's very low above and below the poles. Like this is the north pole, this part is very close to it, right? But this part is in between the N and S pole, that's why it's actually pretty low. So we are going to state that y at y and at z, so we can state that the flux density is greater at y, right, than z. We clear? Okay. Two parallel current carrying wires are placed near to each other in a vacuum. Explain why these wires exert a magnetic force on each other. You may draw a diagram if you wish. Okay, so typically this is the first time I'm seeing this. Typical the drawing is given. This is the first time we have to draw it. Okay, so let's begin. So it isn't like or unlike. So let's just go with like current, yeah. So for example, this is one wire, and this is the other wire. It is carrying current out of the page, or out of this platform, if you will. So if you use a right hand grip rule, you'll see that the field lines, if you point your thumb upward, it's actually anti-clockwise, yeah. So if you draw the fields, you'll realize that the, suppose if this is wire 1 and if this is wire 2, the magnetic field of wire 1 actually interacts with the current of wire 2, and this actually creates a force between them. Do you guys understand what I mean? So basically it's like this. Suppose this is the field line created by this. So it's anti-clockwise, right? I was telling you guys that it's anti-clockwise. It's like this basically. Anti-clockwise. So yeah, at one point it does intersect this. And if you use Fleming's left-hand rule, you know that's FBI, right? Thumb for force, index finger for magnetic field strength, middle finger for current. I'm trying to find out the force on wire 2. So my middle finger is pointing upwards, my index finger is pointing towards the screen, and my thumb is actually pointing towards the left hand side. What does this indicate? That this wire 2 is actually experiencing a force on the right hand side. So on towards the left hand side, towards wire 1 basically. While wire 1 is actually experiencing a force to the right. So for like current, there's actually attraction. So let's describe this. So we need to say that the current in wire creates a magnetic field around the wire. Okay, so the second point is, look, wire 2 actually sits on the field of wire 1, right? So each wire sits on or sits in, that's the wording they use, sits in the magnetic field created by the other. Now, for each wire, the current, or you could say that for each wire, the wire is perpendicular, right? If you see the angle between them, right, what's the angle? Isn't it 90° to the field? Okay, so for each wire, the current is perpendicular to the magnetic field due to the other wire. Okay, so the wires experience a magnetic force. Hopefully that clarifies. All right, there we go. Moving on to question number 7. State Faraday's law of electromagnetic induction. Really common question that you guys will be facing. So Faraday's law states that the induced EMF is directly proportional to the rate of change of magnetic flux linkage. Really common question. Also, guys, if you do like the content, please be sure to subscribe to the channel. It would help me a lot. In the analytics section, I've been seeing that like 89% of you haven't subscribed to the channel, so please do subscribe. It would motivate me to solve more videos. Alright, so please hit the subscribe button if you haven't already. 2 coils are wound on an iron bar as shown. So coil 2 clearly it does not have a power supply, but coil 1 is connected to a power supply. Coil 1 is connected to a potential difference V1 that gives rise to a magnetic field in the iron bar. Figure 7.2 shows the variation with time of the magnetic field or magnetic flux density in the iron bar. A voltmeter measures the electromotive force V2 that is induced across coil 2. So clearly we have to apply Faraday's law of electromagnetic induction as well as Lenz's law. Lenz's law states that the EMF induced will be induced in like such a way such as to oppose the initial change that caused it, because there needs to be law of conservation. The law of conservation of energy needs to be followed, right? So let's begin. Sketch the variation with time of V2. So basically, do you see a positive gradient till 0.15? That means the voltage induced needs to be negative, okay? And we need to check the gradient, okay? Check the gradient. These two lines, right? This red line and this red line, they are parallel, okay? And the one in the middle, it has a negative gradient and it is also steeper. It is also steeper. Okay. So let's begin. For the first part, so if you want to be a perfectionist, you can find out the gradient if you want, okay? For example, this is basically um, 2 boxes in the y-axis divided by 0.15. It's gonna give a high value. Let me bring my calculator. 1 sec. Okay, so it's basically 2 divided by 0.15. which is 40 by 3 or 13.33. What about the blue one? The blue one is basically 4 boxes, right? In 0.15 to 0.25, 0.1 seconds. So that's basically, 4 divided by zero point 0.1, which is basically 40 by 1. So basically the gradient for the second section is thrice the gradient for the first and third section. I've divided the graph into the first, second, and third section. Okay, so the magnitude of gradient in the second section is 3 times the gradient of the first and third section. Also, you need to pay attention to the direction. In the first section, it's actually positive gradient, so we'll get a negative voltage, and vice versa in the second section. Okay, so yeah, they do give a mark for 3 times, because as you can see, this is the gradient for the first and third section, and this is the one for the second section. This is really important. Beforehand they would never pay attention to this, but now they're finally paying attention to that. Okay, so in the first section I took 2 boxes, and in the second section I took 4 boxes. The time for the first one was 0.15 second, the time for the second one was 0.1 second, so it gave me a gradient of 3 times the value. Okay, let's begin. So in the first section we have a positive gradient, so negative value. Okay, and let's see how many boxes do we have here. 2 whole boxes in total. Okay, so I can't use this one because there's 3 times that value is not available. So why don't I use 2 3 4 5 6? This looks good. 2 3 4 5 6, or should I use 3? 1 2 3 4 5 6, 1 2 3 4 5 6 7 8 9. Should I use this? Sure, why not? Alright, so for the first section we have a negative gradient, a positive gradient, so a negative value. So 1 2 3 4 5 6 7 8 9. Okay, so we are going to have a negative value till 0.15 seconds. Then, sorry, it shouldn't be so high up, since it's like 40, the first part should be till 0.15 over here, like this. Next we're gonna have a positive value, because this section is a negative gradient, yeah, so we are going to have a positive value according to Lenz's law, which is going to be 3 times this value. So over here 3 times this original value, like this, up till till 0.25, and then we are going to have the final section, which is going to be a repeat of the original one. This is going to be till zero point 0.4 seconds, yeah, because we have a positive gradient again. Okay, so this is what the mark scheme says. V2 stepped all at non-zero values. It's like a horizontal graph like this. V2 shown with same non-zero magnitude up to 0.15 and after 0.25, but with a different magnitude between these times, between 0.15 and 0.25. The third mark was for saying, or for giving a value that was 3 times the magnitude, and the fourth mark was for giving an opposite sign. Okay, opposite sign. And this is the perfect one, because for a positive gradient you need a negative value. Okay, if you guys want an alternate option, there were other ways to do it. For example, if you wrote it like this, if you drew it like this, 2 boxes, then you could drop to 1 2 3 4 5 6. This was also an alternate option, if you guys are wondering. They would have accepted this as well. This is fine, this is totally fine. Okay, oh my bad there, wait, this was the alternate option that you guys had. 1 2 3 4 5 6, and up to 1 2 over there. Here, this was your alternate option. You'll get full marks for this, no worries. Okay, but I opted for this. This is a better diagram overall, yeah. Okay, moving on. Coil 2 in B is now replaced with a copper ring. So this coil is replaced by a copper ring that rests loosely on top of coil 1. The supply to coil 1 is replaced with a cell and a switch that is initially open. Okay, so now we close the switch. As it is closed, the copper ring is observed to jump upwards. Okay, see what happens. So when we close this, current flows through this wire, yeah. As a result, there was no flux initially, but suddenly there a flux is generated, like the field, there's current in this wire, so it actually, if we apply, you know, the right hand grip rule, it can be seen that the field lines are like this basically. So these new field lines actually cut the cut the copper ring. As a result, there's a change in flux linkage in the copper ring. As a result, you know, an EMF will be induced, and it will be induced in such a way that it opposes the initial EMF which created it. So if the field is like this, like if the field is like this, for example, okay, if it's like this, we know that this is the north pole according to the right hand grip, and this is the south pole. The ring will have such a magnetic field so as to oppose the change that created it. So this will be the south pole and this will be the north pole. Okay. As a result, what force will be generated between them? Repulsion. That is why it appears to jump upwards. But after some time, it won't jump upwards because there is no change in flux anymore. The flux in the ring will become constant, so no more EMF will be generated. Do you guys understand what I mean? So let's see, let's explain what happens. So changing current in coil causes changing magnetic field. Okay, this is just for the initial stage though. When you just close the switch, it will create a changing field, or you could just directly say that, you know, the changing, there's a change in flux, right? The changing flux, changing magnetic flux causes induced EMF in ring. That's our first point. You could write either one. So what does this induced EMF actually do? So the induced EMF in ring causes a current in ring. So we know that with EMF induced, current will also be induced, and whenever there's current flowing, a magnetic field will be created. So the magnetic field will be created in such a way such as to oppose the initial change. So that's your second point. This is your second point. This was your first point. Now for the last point, what do we have to write to get 3 marks? So the third point entails the magnetic field due to induced current in ring interacts with the coil's field to cause an upward force on the ring. Okay, or you could say this, that the induced current in the ring is perpendicular to the coil's magnetic field. The coil's magnetic field, which causes an upward force on the ring. Yeah, there you go. It's a really important question. Okay, everyone should learn this properly. But it would fall down again in a bit, right? It won't jump. It would jump upwards then come back. Now suggest for the reason, what would be the effect when repeating the procedure with the terminals reversed? What if we had it like this? This was the positive and this was negative. And no change, guys. Basically, if you did reverse the terminals, essentially what would happen is, wait up. Basic current would flow in in different directions like this. Okay, it would be like this basically. So if you did use right hand grip rule, this would be the north pole and this would be south pole, but it would be induced in such a way such as to oppose the change. So this would be north and this would be south, right? There would still be a repulsive force, it would still jump upwards. So basically no change. This was just a trick question. The correct answer should be both magnetic fields reverse direction, so ring still jumps up. Okay, or the current in ring and coils field both reverse, so ring still jumps up. Yeah, okay, this is important. Okay, moving on to question number 8. Experimental evidence for particulate nature of electromagnetic radiation. That's, we know that it's the photoelectric effect basically. Yeah, and the wave nature of matter. So in the first one, a wave acts as a particle, and the second one, a particle acts as a wave. So we can see that in electron diffraction. Okay, we can see that in electron diffraction, like when we do pass a beam of electrons through a specific slit, we know that it's particle in nature, so we were supposed to see dotted particles, right? But after you pass it through a specific slit, do you know what we're gonna see? Kind of like in the experiments of Young's double slit and the diffraction grating. Remember, we used to get specific patterns. So we actually get a pattern of concentric circles. This was completely atypical for particles like electrons. We were supposed to see particular spots where the screen lights up, but we see a specific pattern of concentric circles. So this indicates that the electron, which was initially a particle, the beam of electrons, after passing through the specific diffraction grating, it has turned into a wave. So this is evidence for the wave nature of particles. All right, this is very important. Calculate the de Broglie wavelength of an alpha particle moving at a speed of 6.2 to 10 power 7. So we know that we're going to use de Broglie wavelengths from the de Broglie wavelength, which is lambda is equal to h Planck constant by p, the momentum. So let's find out um, lambda. So lambda is going to be 6.63 into 10 power minus 34. That is the Planck constant. And what about the momentum? We know that an alpha particle has a mass of 4u. So the momentum should be P is equal to mv, which is 6.2 into 10 power 7 into 4 times 1.66 into 10 power minus 27, right? 6.2 into 10 to the power 7 times 4 into 1.66 into 10 power minus 27, which is 4.1 into 10 to the power minus 19. Okay, let's use that. 6.63 into 10 power minus 34 divided by answer. 2 SF, I'm getting an answer of 1.6 into 10 power minus 15. 1.6 into 10 power minus 15. Okay, great. The speed of alpha particles is gradually reduced to 0. On figure 8.1, sketch the variation of v with lambda. Okay, check this. We know that lambda is equal to h by p, or lambda is equal to h by mv. So lambda is equal to h by m into 1 by v. H, Planck constant, is a constant. Mass of the alpha particle is also constant. So we can say that lambda is proportional to 1 by v. So they are inversely proportional to each other. Okay. So it's going to be an asymptote on both sides. Okay. So it can never touch the y-axis, and we know that when the speed is 6.2, it has a value of 1.6 into 10 to the power minus 15. Okay, so basically it's going to be like this. It can't be 0 basically. It's going to be really low, but not 0. Yeah, just have to draw. Non-zero. Don't make it touch the x-axis, okay? Basically, that's what you need to know. Like this, right? Suggesting explanation why people are not observed to deflect when they walk through a doorway. Interesting question. Basically, the door is also acting as a diffraction grating. Like electrons became waves. Why not people? Basically, the smaller the particle, the easier it is to diffract. Uh, Theoretically, it's possible for people to turn into waves, but practically it's impossible because the diffraction grating, like the smaller the particle, or the bigger the particle, the smaller the diffraction grating has to be. So it's actually quite impossible. Basically, we can say that the gap in the door is not small enough, essentially. And it's actually impossible to form a grating that's, um, possible. It's impossible to form a grating that will allow people or humans to diffract. Like it's impossible for a tennis ball to diffract. So humans are like far away from diffracting. Okay, so what makes diffraction possible? Essentially, we know that lambda is equal to h by mv. So think about the mass of people. The mass is really high, right? So if this increases, what happens to wavelength? It decreases by a lot. Okay, so the de Broglie wavelength for people would be too small, essentially. And the width of the doorway might be 1 meter, right? So they need to be comparable for good diffraction to take place. You've learned this in AS physics. For good diffraction to take place, the width of the slit must be comparable to the wavelength, then good diffraction takes place. But compared to the width of the doorway, our it's like this. Compared to the width is really huge. The wavelength is minuscule. It's like this. No diffraction would take place. So that's why it's impossible. Okay. So essentially, the de Broglie wavelength is negligible compared to or compared with the width of the doorway. Right? Everyone lost their minds after seeing this question. All right. Okay, so that's it. Moving on to question number 9. Okay, for 9, this is the new section that's been added from 2022, astronomy, right? So state Hubble's law. So Hubble's law basically states that the speed is directly proportional to the distance. As you can see from here, wait, let me show you. We have the constant. Wait, no, we don't actually. Okay, my bad. So Hubble's law states that the speed is directly proportional to distance. What does this speed mean? It's actually the speed of recession. So suppose we're an observer on Earth. So this speed is basically the speed of recession of a galaxy away from us, okay? And it leads to the redshift, where the speed is the speed of recession. Speed of recession basically means like something that's going away from you, okay? Receding. Like maybe an ambulance is going away from you, that's the speed of recession. Where speed is the speed of recession of the galaxy from an observer, and distance is the distance of galaxy away from the observer. So basically, the further away the galaxy, the greater the speed of recession. You could also word it like this: the speed of recession of galaxy from the observer is proportional to the distance of the galaxy away from the observer. I think that's a better way to write it down. What do you guys reckon? So let's do that. Let me move this over here. A lot of you have been requesting this paper. Sorry, I wasn't able to solve it. So the speed of recession of a galaxy from the observer is proportional to the distance of galaxy away from the observer. Okay. Explain how cosmologists use observations of emission spectra from stars and distant galaxies to determine that the universe is expanding. So basically, since there's redshift, what will happen is like light or the emission spectra that we observe from a distant star, the wavelength will actually be greater than the actual one. The observed wavelength will be greater than the expected one, essentially. This shows that the galaxy is actually moving away from us, or the universe is basically expanding. Because if it wasn't expanding, then the value was supposed to be the same. You learned this in AS physics, like when an ambulance moves away from you, the wavelength actually increases and the frequency decreases, right? So that's redshift, essentially, because we know that it's Vib years. So basically, this is 700 nanometers. This is around 380. It's going towards the greater wavelength. Wavelength is increasing. That's why it's called redshift, right? So the wavelengths of spectral lines are greater than the expected values, or greater than their known values. Suppose we know that that a star is composed of hydrogen. So the spectral line for hydrogen is supposed to be something like 420 nanometers. But when we observe it from the star, we're getting something like 450 nanometers. Why are we getting a greater value? That doesn't mean something is wrong with hydrogen. Rather, since the universe is moving away or the universe is expanding, we're getting a greater wavelength. Okay. So redshift shows that stars in distant galaxies are moving away from Earth, right? Are moving away from Earth, right? So moving on to the next one, explain how Hubble's law and the idea of the expanding universe led to the Big Bang theory of the origin of the universe. All right. So basically, we know that according to Hubble's law, the speed of recession is equal to or proportional to the distance from the observer. And since distant objects are moving away faster, what does that indicate? That matter must have been very dense in the past. Okay, the Big Bang theory states that it all started from one single explosion and it has never stopped expanding. The origin was an explosion and it has been going on for a long time. So Hubble's law states that the speed is proportional to the distance. And the idea of the expanding universe means that there is no end to it, that all the parts of the universe are away from each other. So I'm going to refer to the second answer first. We can say that all parts of the universe are moving away from each other. Do you guys get what this means? It should not be relative to the Earth. Like if you are on a different planet like Mars, it will seem like everything is moving away from Mars. Okay, so this is the reference of the second answer. Now about the first one, we can say that more distant objects are moving away faster, right? This is a reference to, you know, Hubble's law. So what does that indicate? This indicates that matter must have been very close together, or we can say that very dense in the past. Do you guys understand? So yeah, this was a new question. This hasn't been seen before. So this is really important for you guys, okay? That's the problem with new syllabus content. You never know what's coming, yeah? But it's fine. You guys have enough content from 2022 onwards for your exam in 2023. Moving on to the last question, right? What do you mean by radioactive decay? So it refers to the spontaneous emission. It's a natural process of ionizing radiation from an unstable nucleus, right? So a radioactive sample consists of an isotope X of half-life T that decays to form a stable product. So the stable product does not decay anymore. Only X and the stable product are present in the sample. At time t is equal to 0, the sample has an activity of A naught and contains N naught nuclei of X. On figure 10.1, sketch the variation with time t of the number of nuclei of X present in the sample. Okay, so at time 0, it has 1 N naught. After one half-life, it becomes half of its initial value, which is 0.5 of X basically. X is the radioactive sample, okay? So after another half-life, it becomes half of that. Half of 0.5 is 0.25. You guys know that. Half of 0.25 is 0.125. So 0.125 is basically 0.125, which is over here, 0.125 N naught. Okay, so this is what the graph should look like. So is that it? That seems too easy. It's a bit hard for me to draw on this platform. Okay, here you go. This is what it looks like. Negative gradient. Last part. On figure 10.2, sketch the variation with n of the activity of the sample for values of n between n is equal to n naught and n is equal to 0 to n is equal to n naught. So think about it. The equation for radioactive decay is n is equal to n naught e to the power minus lambda t. Okay. So activity also follows the same equation. A is equal to a naught e to the power minus lambda t. It's the same thing basically. So what do they want us to do here? It's not a relationship with time, sadly. It's a relationship with n naught. So you guys need to understand that n naught and a naught, or n and a, are proportional to each other. Do you guys understand? So when we have higher number of particles, we will also have greater activity, because you guys know the equation connecting them, right? What's the equation connecting these two? A determines activity. Okay, A determines activity, and n determines the number of unstable nuclei. All right, so the relationship between A and n is basically A is equal to lambda n, right? That's the relationship between activity and the number of unstable nuclei or radioactive nuclei. So obviously, for the initial number of unstable nuclei, we are going to get the initial activity, okay? Also, think about it. When the number of unstable nuclei is 0, A naught will also be equal to 0. So we got our 2 points. We know that when A is 0, N is also 0. We also know that when we have 1 times the number of unstable nuclei, we will also have 1 times the initial activity. Okay, it's a given. So since we got these 2 points, and if you make this relationship, make A not the subject, or if you make like if you move A naught and N naught on one side, basically A naught by N naught, or you know, this shouldn't be referred to as naught. Okay, it's just A and N. So A by N is actually equal to lambda. So it's gonna be a straight line which passes through the origin. Basically, it's a straight line passing through the origin. Okay, makes sense. So state the name of the quantity represented by the gradient of your line in C1 and C2. Okay, C2 is pretty straightforward. Since we know that A by N is the gradient, it is actually equal to lambda, which is the decay constant, right? It's the decay constant. What about C1 though? The gradient or the tangent of this line. Okay. Okay, so the gradient is basically the rate of change of N, right? With respect to T. So the rate of change of N is actually the activity. You guys need to remember that. Del N by del T is the activity. So the gradient of this graph refers to the activity, right? This is very important because the equation for this line is actually N is equal to N naught e to the power minus lambda T. Okay, this is the equation for the graph. Now if you do, convert it to a linear relationship. Actually, let's not do that. Let's not convert it to a linear relationship. Then we're gonna get something else entirely. You don't need that. Just remember that activity is the rate of change of the number of unstable nuclei. Okay, very important. So it's activity. Okay, last. For the sample in B, calculate the fraction n by n naught at time. Oh, this is exactly what I was talking about. We know that n is equal to n naught e to the power minus lambda t. So n by n naught, if we bring them to one side, we end up with e to the power minus lambda t. So it's basically n by n naught is equal to e to the power minus. Do we know the value of lambda? Okay, so time is 1.70. Okay, so we don't know the value of lambda, but the time is given in terms of capital T. So this was a tricky question because the time here, this time is the time required for it's the one half-life essentially. So it's basically 1.70 times one half-life. So you guys know that radioactivity is a first order reaction. So the half-life is actually equal to ln 2 divided by lambda, right? So what is lambda equal to? You know that lambda is equal to ln 2 by half-life, and the half-life happens to be capital T over here. So can we write this, that in the place of lambda I can write minus ln 2 divided by capital T times, in the place of time we can write 1.70 times T. So we can get rid of these capital T's basically, and we end up with n by n naught is equal to e to the power minus ln 2 times 1.70. Let's find that out. Ln 2 times 1.7 e to the power minus answer. So I'm getting an answer of n by n naught is equal to 0.31 to 2SF. Okay, really interesting question. Okay, first time I'm seeing it. So that's all, guys. Glad, hope you liked the video. So I'm gonna link the paper for May-June 2022, variant 4.1 or 4.3 up here. I'm going to link the playlist for paper 4 up here, and I'm going to link the paper for February March 2022, variant 4.2 down here. Alright, and be sure to subscribe to the channel if you like the content. Also, there was a problem in May-June 2022 4.1 or 4.3 that I wasn't sure about. I mentioned that in the video. So let me show the explanation here. So basically it was in variant 4.1 where I wasn't sure about the direction of flow of current. Okay, wait, let me show you. Yeah, okay, it was this question over here. So in that particular question, I wasn't sure why the current was flowing in that particular direction. Like, why was it anti-clockwise and not clockwise? This is very important. So I linked a reference video for Khan Academy down there that explains it pretty well. I totally overlooked this while I was solving it. Okay, so this was the question. The procedure in B is repeated, but this time the terminals of the coil are connected together. State and explain the effect on the coil of connecting the terminals together during the change of magnetic flux density, shown in figure 6.2. Okay, so basically when you do connect the coil together, beforehand current was not allowed to flow, because the terminals were not connected. But now when you do connect them together, current will be allowed to flow between the terminals. So what I was confused about was the direction of flow of current. So let's do that. To do this, you need to follow the left hand rule and basically the Lenz's law. Okay, so use your left hand. So the magnetic field lines are into the page, so your index finger should point into the page or into the screen. Okay. Now, here's the question. So there was a change of magnetic flux density, right? So we know that according to Faraday's law, an EMF will be induced when there's a change in magnetic flux in the coil, right? That's what happens essentially. So about the direction of the current, okay. Basically, rather than thinking about the direction of the current, you need to think about the direction of the induced magnetic field. Basically, think about it. Inside this coil, the magnetic field is directed inwards, okay? So, our magnetic field will be induced in such a way such as to oppose this change according to Lenz's law. Okay, so that means that the current that your wire will produce cannot have a magnetic field that's pointing into the plane. It has to point outside the plane, or else there won't be, like, it won't oppose the change that created it. If you create a field that also points inside the field, that would be weird because it doesn't follow the law of conservation of energy. It would be producing more energy. So our field has to be induced in such a way so that it opposes the original change. So the field produced by our coil should actually be outwards. It should come out of this plane. Do you guys understand? Okay, now what? Now you need to use the right hand grip rule. You know that when current flows through a wire, it creates a field around it, and we actually use the right hand grip rule. For example, what if, guys, I try clockwise current? Okay, what if I try clockwise current? So if you use your right hand grip rule, your thumb should point downwards. So look at the field lines. The field lines are kind of like this. the field lines are kind of like this. If you do point them down, if you point your thumb downwards, your other four fingers should point inwards into the plane. That can't be possible, because then that would actually follow the direction of the given field line. But think about it. What if you induce the current in this way, anti-clockwise nature? Now what? If you use a right hand grip rule, your thumb should point upwards and look at your fingers. The four fingers are appearing as if they are coming out of the plane. It's like they are coming out of this plane, kind of like this. They're coming out, right? This is what your fingers should look like when you use the right hand grip rule. Okay, the fingers appear to be coming out, and basically because the magnetic field line given points inward inside this plane, okay, the magnetic field lines are supposed to come outward to oppose that change. It's a bit tough to understand without diagrammatic representations. It's hard to show you. The explanation is given better in the Khan Academy video, but let me show you in a 3D manner. So basically this is the plane, for example. Now the field line over here is out of the plane, right? I am viewing this from the side. So our induced magnetic field must be in such a way such as to oppose the change, so it should point downward. So if if your arrow is induced in this way, check it out. What happens? Sorry, they go into the page, right? My bad. The given field is going into the plane. So our field must come out of the plane. So if you point your right thumb in this direction, you'll see that the field lines are coming outside like this. Doesn't that make sense? Coming outside from here, it's opposing it. But if the arrow, if you draw it in this way, point your right hand towards that direction or towards this direction, it won't match. It will seem as if the arrows are pointing downwards into the plane. That can't be possible. Energy won't be conserved, okay? That is exactly why the arrows must be pointing in an anti-clockwise direction like this. So our produced field opposes the given field, okay? Now what's the next section after finding out the direction of flow of current? Basically, you can apply Fleming's left hand rule now. How? Put your index finger into the page or screen, middle finger upwards. I'm talking about this side. The force is towards this direction. F is towards this direction. What about the one at the top? Middle finger, index finger inside, middle finger to the left. The thumb points downwards. Now this side, middle finger in, sorry, index finger in, middle finger down, the thumb points to the right. Last section, index finger inside, middle finger to the right, force points inwards. So basically it seems as if the force is trying to pull the square coil inwards. It feels an inwards force, okay? So that was the explanation of the third point, and it was really complicated, right? So the induced EMF causes a current flow in the coil because it's connected, the terminals are connected. The current causes dissipation of energy in the resistance of the coil. Okay, so the temperature of the coil rises. That is one way of answering it. I wasn't able to answer the pink section in my previous video. The current in the magnetic field causes a force to act on the coil. Okay, now what about the force? The opposite sides of the coil is forced inwards. This is the exact reason why it happens. Could I clarify? But guys, if the magnetic field was out of the page, the opposite would have happened. Okay, they would be pointed outwards. Okay, thank you. And if you do have any other questions, please let me know. So yeah, as I was saying, I'll link these videos over here. May June 2022-4-1 up top to the right, paper 4 up top to the left, Feb March 2022-4-2 down here. And remember to subscribe to the channel if you like the content. See you guys.